In today's session, we continue with the numericals on traveling waves. So the first question is, this is from one of the GATE question papers. So in the figure, in the question, you are also given this figure. This is the point P and load resistance 300 ohms and ZC is 300 ohms. So we have to now find the reflection coefficient. Please observe there, you have the load impedance same as characteristic impedance. If load impedance equal to characteristic impedance, then reflections do not occur in a transmission line. If reflections do not occur in a transmission line, then the reflection coefficient is 0. What about the reflection coefficient? The reflection coefficient is 0. Next question is from the GATE question paper. An overhead line having a surge impedance of 400 ohms is connected in series with an underground cable having a surge impedance of 100 ohms. If a surge of 50 kV travels from line to junction, so transmitted voltage wave at the junction is so how you find what is the transmitted voltage? It is V double dash. How to find what is V double dash? V into first we are having cable, so 2 times Z cable divided by ZC plus Z cable. Please refer the equation 3 of condition 4 in the yesterday's session. So this is the formula. So now you substitute this one. V is 50, cable 100, ZC is 400. So on simplifying this one, You get the answer as 20 kV. So what is the answer you get? 20 kV. Now solve this next question. This is from the IES question paper. A traveling wave due to lightning with an incident voltage V travels through the overhead line of surge impedance 400 ohms and enters a cable of surge impedance 40 ohms. The voltage entering cable is. So similar to the last question, find out V double dash. V into 2 times Z cable by ZC plus Z cable. And V how much? Not given, so you get the answer in terms of V only. 2 into 40 by 400 plus 40. So I'm simplifying, how much you get? You get 2V by 11. So what is the answer you get? 2V by 11. Now we solve this next question. These also from GATE IES question paper. A surge voltage rising at 100 kV per microsecond travels along an open circuited transmission line. It takes 10 microseconds to reach open end. The reflected wave from open end will be rising at. From the open end will be rising at. So how to find out this one? So reflected wave, you have open circuited transmission line with the receiving end operating under open circuit condition. We know voltage at the open circuit receiving end increases by same V. So at what rate it will increase by? The same 100 kV per microsecond. This based on the statement you have written for case 1. With the receiving end operating under open circuit condition, voltage at the open circuited receiving end increases by V, that is 100 kV per microsecond. Now we solve this next one. A surge of 15 kV magnitude travels along a cable towards its junction with an overhead transmission line. The L and C of cable and overhead transmission line are 0.3 millihenries, 0.4 microfarads, and 1.5 millihenries, 0.012 microfarads per kilometer. The voltage rise at the junction due to surge is. So in this question you observe the important point. Wave is first traveling through cable, further through overhead transmission line. Our analysis, wave travels through the line first, further through cable. But here the question data is represented reversely. First through cable, further through line. So how you modify our formula now? V double dash is V into 2 times ZC by Z cable plus ZC. How to find out these two impedances? ZC and Z cable, you know the formula is under root L by C. First to substitute for cable, 0.3 millihenries, 0.4 microfarads. You get 27.38 ohms. Next check for a line, 1.5 millihenries and 0.012 microfarads. How much you get? 353 ohms. So on simplifying this one, how much you get? 15 into 2 into 353 by 27.38 plus 353. So how much you get? 27.87 kV. You get 27.87 kV. Now we solve this next question. This is from a GATE question paper. Consider a step voltage wave of magnitude 1 per unit traveling along a transmission line within the brackets it is given lossless that terminates in a reactor. The voltage magnitude across the reactor at the instant traveling wave reaches the reactor is. So in the figure, even this figure is given. So this is the reactor figure here. Now observe here, you are having a lossless line. The point required to solve this question is reflections do not occur in a lossless line. As reflections do not occur in a lossless line, what will be the transmitted wave? Same as incident wave. How much that incident wave is given? 1 per unit. So what will be the transmitted wave? The transmitted wave is also 1 per unit. So we are dealing with a lossless transmission line. Reflections do not occur in a lossless transmission line. So transmitted wave is equal to incident wave, that is 1 per unit. You get the answer as 1 per unit. Now we solve this next one. Is a common data question. A surge of 100 kV traveling in a line of natural impedance 600 ohms arrives at a junction with two lines of impedances 800 ohms, 200 ohms. First part of the question is transmitted voltage is. So how to find V double dash V into 2 by ZC 1 by Z1 1 by Z2, 1 by ZC. So V is given as 100 kV, ZC is 600. So accordingly you calculate this one. So on simplifying, how much you get? 42.04 kV. Next is the transmitted currents. What are the transmitted currents? We have I1 double dash, V double dash by Z1. Z1 how much? 800 ohms. So V double dash is 42.04 kV. Z1 is 800. How much you get? 52.55 amperes. How to find second transmitted current? I2 double dash, V double dash by Z2. Z2 is 200. On simplifying, you get 210.2 amperes. Answer is 210.2 amperes. Similarly, we solve this one. This is from a GATE question paper. So how to find the voltage? Formula is the same. So but that first you calculate what is Z1 and further Z2. But observe, in the question it is given first cable and followed by two identical transmission lines. So how you modify our formula? This is for first width line followed by cable. So first itself, if you have cable, what you write? 2 by Z cable divided by 1 by line ZC1, other lines ZC2 and cable. Only these how you have to modify. Now how to find what is ZC1 or ZC2? Under root L by C. L 1.5 millihenries, C 0.015 microfarads. So on simplifying this one, you get 316.22 ohms. Next is corresponding to cable. Cable how to write? Under root L by C. For cable what you write now? 0.4 millihenries and 0.5 microfarads. On simplifying this one, you get 28.28 ohms. So now we substitute these values and calculate. So 20 kV, 2 by this value, 1 by 316.2, again 1 by 316.2, 1 by 28.28. On simplifying, get 33.93 kV. So the answer is how much? 33.93 kV. So this is how you solve the last part of that question. Now we solve this next question. This is from a GATE question paper. A lightning stroke discharges an impulse current of 10 kiloamperes peak on a 400 kV transmission system having surge impedance 250 ohms. The magnitude of transient over voltage traveling waves in either direction assuming equal distribution from the point of lightning stroke is so impedance how much it is given 250 ohms. Now you check here, you have a transmission line. Lighting impact of 10 kiloamperes is exactly at the middle. So how much after the impact takes place, how much current flows on either side? 5 kiloampere each flows on either side. 5 kiloamperes flows on either side. But what is the impedance of the line on either side? ZC 250 ohms means not the total is 250 ohms. At each and every point on the transmission line, the characteristic impedance of transmission line is 250 ohms. So to the left side, it is 250 ohms. To the right side also 250 ohms. So how to find out what is the voltage? Transient over voltage. So how to find out this transient over voltage? It is given by I into ZC. So 5 kiloamperes, ZC is 250. On simplifying this one, you get 1250 kV. On simplifying, you get 1250 kV is the corresponding answer here. Now we solve this next one from the IS question paper. The L by C ratio for 132 kV and 400 kV lines are 160 into 10 cube and 62.5 into 10 cube. The natural three-phase loading for the two lines is. So how to find out for the first line? What do you mean by natural three-phase loading? Natural three-phase, natural impedance also known as surge impedance. So natural three-phase loading means the surge impedance loading. It is the surge impedance loading. By default you calculate for three-phase only. So substitute the line-to-line voltage. So first to find out for transmission line 1, what is the formula? V square by ZS, or ZS is under root L by C. For 132 kV, L by C how much? 160 into 10 cube under root. So this is what we have to solve here. And similarly, for transmission line 2, formula is the same, V square by ZS. How much V is now? 400 kV. But ZS is still under root L by C. What about the denominator? 62.5 into 10 cube under root. So this is what you have to calculate here and find out what is the surge impedance loading or the natural three-phase loading for the two transmission lines. So these are the questions based on the 5 conditions and the basics of traveling waves. Now we discuss the next topic. You know that voltage wave travels from sending end to receiving end of a transmission line. Current wave travels from sending end to receiving end of a transmission line. So now we check what is the velocity at which voltage wave travels from sending end to receiving end and current wave travels from sending end to receiving end of a transmission line. So the next topic is velocity of traveling waves. On simplifying, you get the characteristic impedance also further. Okay, you consider a transmission line, and in this transmission line, you consider a very small section dx. Say the length of the transmission line is x. Length of the transmission line is x. So consider a section dx of transmission line, and x is the total length of the transmission lines. Now for this very small section dx, how you find the total charge enclosed? Charge, how you write? C into V. For very small section you write C into V dx. So first we mention the total charge enclosed by the section dx. How to write? dq C into V dx. Then how you find what is the total charge enclosed? Q, how you write? We integrate dq between 0 and x. So on simplifying this one, how much you get? Cv into x. Once you know the charge, you can find current. So what is current flowing through transmission system? We have to check now. So what is the current flowing through the system? I equal to dq by dt. So d by dt of Cv into x. So Cv into dx by dt. What is dx by dt? Velocity. Now we check related to flux linkages. How to find the flux linkages? L into I. For the very small section dx, the flux linkages outright L into I dx. So now you mention the flux linkages for the section dx. How to write? d psi is L into I dx. Now you check the total flux linkages. Psi, how to write? You integrate this. On integrating, how you write? Li into dx. So you write Li into X. Now once you know the flux linkages, how you check the voltage? Voltage is the rate of change of flux linkages. Voltage of, you write voltage across the transmission line conductors. V, how you write? D psi by dt. D by dt of Li into X. So Li into dx by dt, how much here? Velocity. So now how to find out velocity? Multiply the equations 1 and 2 now. So I is Cv into V. V how much? Li into V. So this side Vi, here also you take out Vi, you get Lc into V square. So Vi gets cancelled. From this you find out what is V. How much? 1 by root Lc. So what is V? 1 by root Lc. So this is the formula to find the velocity of travelling waves. So this formula is important, the velocity of travelling waves. Assign this as the equation 3. Now further, if you analyze, you get the other formula as 3 into 10 power 8 meters per second divided by under root epsilon r. This other formula to find out the velocity of travelling wave. What is epsilon r? Relative permittivity of the medium. Relative permittivity of the medium. Now further, if you divide these two equations, 2 and 1, so what is V? Li into V. What is I? Cv into V. So on simplifying, V square by I square is L by C. What is V by I? Z. Which impedance? Impedance of transmission line. So what is the impedance of transmission line? Zc, how much you get? Under root L by C. So not only Zs, Zc is also under root L by C. So only in any calculation, as Zs values are never known, you substitute Zc values only. So in any calculation, you require say Zs. As Zs values are never known, we substitute Zc values instead of Zs. So this is how you check and find the velocity of travelling waves. The equations 3, 4 are important. The different formats of representing the velocity of travelling waves. Now we solve this next question. This is from a GATE question paper. The velocity of propagation of electromagnetic wave in an underground cable with epsilon r equal to 3s. So what is the formula for us? 3 into 10 power 8 by under root epsilon r. So simplify this one. You get root 3 into 10 power 8 meters per second. Root 3 into 10 power 8 meters per second. Now the next question is, this is from the GATE question paper. A cable has following characteristics: L 0.201 microhenries per meter, C 196.2 picofarads per meter. Now we find the velocity of wave propagation through the cable is. So how you find the velocity? Formula is 1 by root LC. You know the value of L, 0.201 micro, C 196.2 picos. So on simplifying this one, you get the answer 159.24 meters per microsecond. So on simplifying, this is the answer you get. Now you have 5 minutes break. First question is by Sirisha. In the sixth problem, as reflections do not occur, transmitted wave is 0. No, transmitted wave is incident wave plus reflected wave. Reflections do not occur, so reflected wave 0. Therefore, transmitted wave equal to incident wave 1 per unit. Next question is by Arijit from Kolkata. Now in question number 5, we have a cable and line further. Now our analysis, what we did in the yesterday's session is, first we have a transmission line, further cable, and we know V double dash formula. Now you modify the formula considering the cable first and line further. And in a lossless line, alpha is 0. And not only alpha 0, the reflections do not occur in a lossless transmission line, because it is one of the properties of a lossless line. Next question is by Sirisha. Please explain third question in velocity of traveling waves topic. 13th one, velocity is given by 1 by root LC. So based on that, you substitute L and C and calculate. Next question is by Anupam. How dq is C into V dx? See, q is how you write CV. For very small section, dq is C into V dx. Next question is by Shailesh from Bikaner. What is the domain of power systems? Is it from generating station to distribution transformers, or till domestic electricity? Till the domestic electricity, please. Yeah, please continue, please.
Sir, if the examiner asks to find out characteristic impedance and as well as surge impedance, then how to calculate? So we are getting same formula for both surge impedance and characteristic impedance.
No, anytime you will be questioned to find only one place, either characteristic impedance or surge impedance, either CIL or SIL.
But definition-wise, both are different, but formula-wise we are getting both.
But
same.
ideally, you don't have any value for ZS or SIL. So we treat same as characteristic impedance and substitute the same value for surge impedance. Definition-wise,
numerical-wise, both are same.
Different. Yes, please.
Numerical-wise, both are same.
Same value, please.
Okay.
Right. Next question is by Purushottam Kumar. In question number 5, V double dash. Our V double dash formula is V into 2 times Z cable by ZC plus Z cable, or V double dash is V into 2 by ZC by 1 by Z1 plus 1 by Z2 plus 1 by ZC. Suppose you have a cable first and line further. Accordingly, you modify the formula. V double dash is V into 2 by Z cable divided by 1 by ZC1 plus 1 by ZC2 plus 1 by Z cable. Okay, we continue with the next questions. These asked in one of the GATE question papers. total reactance and total susceptance of a lossless overhead transmission lines operating at 50 Hz are 0.045 per unit, 1.2 per unit. If velocity of wave propagation is 3 into 10 power 5 kilometers per second, then approximate length of transmission line is